It's on. All right, so here's our 2 poll questions. First one goes back to if you get a fraction with one term in the denominator, what you're going to always want to do, and I would say the same thing is true with derivatives, so that you don't have to do an ugly quotient rule, is split it up. Split it up into 2 fractions. Okay, that's when you have one term in the denominator. One term in the denominator. You're going to split that up. And split up. So that's going to give us, where's my good pen? There it is. And you're going to just use your rules of exponents. 6x to the 4th divided by x squared really just gives me 6x squared. This is 1 over x squared, but if I'm getting ready to use my power rule for antiderivatives, I'm going to want to write that as x to the negative 2. And then for my antiderivative, yeah, I saw the discussion today. Generally, this is just like generally speaking, however they define the function with a lowercase, you just make the uppercase, and that's generally understood to mean you're finding the antiderivative of this function. So for a function like this, remember constants if it's multiplied by a constant, that just gets to stay there. Your power rule, you're going to add 1, divide by that same power. So here it's going to be x to the negative 1 over negative 1. And then don't forget to put plus c, because in fact, one of my distractors, I call a distractor, one of the answers you could have chosen that was incorrect, but not really that incorrect, just didn't have the c. So this simplifies to 2x cubed. I could apply this negative 1, right? If you're divided by negative 1, you could just put that out in front. This minus right here, and then x to the negative 1 is really just 1 over x plus c. So this was the correct answer. I don't remember what number it was. But I know one of them I had was that without the plus c. So that was just to remind you to always put the plus c. Okay. One of the incorrect answers that I know some people chose is what you would have gotten if you just found the antiderivative of the top and divided it by the antiderivative of the bottom. So make a special note of that. If that's the answer you chose, remember, you can never do that, okay? Just like with derivatives, if you had a fraction, you can't expect to just take the derivative of the top and divide it by the derivative of the bottom. Same thing for antiderivatives. It's not going to work. So this would be the way to do it. All right. And then the second question touches on what we were discussing a little bit on Monday as well. The idea of when you're finding antiderivatives, acknowledging the chain rule in reverse, okay? I only had 3 options here. One of the options, the choices that you could have made was actually the derivative of this. And I did that intentionally too, because it is a little bit frustrating. You got so used to taking derivatives of everything last quarter, it's kind of a natural thing to mistakenly take the derivative rather than the antiderivative as we move into 17b. So don't feel bad. That happens very, very common, because the derivative of e to stuff would have been e to stuff times the derivative of the stuff, which is 4. But the antiderivative of e to a constant times x is going to be e to the 4x divided by 4, or times 1/4 if you're using one of Professor Burke's formulas. Okay, same thing. And that idea, when you have a constant times x where you're going to be dividing by the derivative of 4x, it applies throughout all these different functions. So this isn't just cosine of x, this is cosine of pi times x, which is just a constant. My antiderivative for the cosine function is sine, so it's going to be sine of pi x, not times pi. That's what happens when you do the derivative. It's going to be divided by pi. And then you'll have to get used to this too. The derivative of sine is positive cosine. The antiderivative of sine is a negative cosine. And the same deal, if it's a constant times x, it's going to be 0.5x technically divided by 0.5. And to see the correct answer I had, what you would have to do is realize that when you're dividing by 0.5, right, 0.5 is really the same as 1/2. So if you're dividing this by 1/2, that's the same as multiplying it by 2. So it's really -2 cosine plus c. I might as well share this with you now. Oh, and then I heard the discussion that Dr. Burke said was, you can use any letter. If you felt like you used a C somewhere else, then switch it to a plus K. I haven't seen anybody get marked down for just leaving it as plus C. You can use whatever letter you want, though. But a very, very common mistake, you can probably anticipate this on the first quiz in 17B, is you might get 2 or 3 antiderivatives, and I get students who come to me afterwards and they're all bummed out, and I'm like, what'd you get on your quiz? Like, I got 19 out of 20. I'm like, well, why are you upset? They said, yeah, well, you know how I lost my point? I forgot to put the plus C on both of my answers, and she took off a half a point, right? It's an easy mistake to make. So here's how you're going to remember this. You ready? After you figure out this antiderivative for this function, which requires a little thinking, right? You got to think about the chain rule in reverse and all that stuff. And you're pretty sure that you got the right answer. What do you usually say to yourself inside? Don't you say, like, if you're pretty sure you got it, you say yes, right? You're like inside, you're like, yes, I got this one. I know I got that one. So when the quiz comes up, if you've got some antiderivatives and you get to this part right here, you get to right there. When you get to the yes part that you're going to say inside, say it in Spanish. I know it's a little funny, but yeah, but don't write it in Spanish. But if you say it in Spanish, right, C, then you might remember to put your plus C at the end, okay? I guess you could say it in French or whatever. Okay, yeah, sorry. Yeah, I know. Math humor is a little bit weird. I know. Just got that. Okay. Other thing I want to remind you of is, and we had talked about this on Monday as well, is remember that if you're not sure if this is the right answer, if you're not sure, you're like thinking, wait, should I have been dividing by pi? Should I have been dividing by 4? How can you always check your answer? Is if you're not sure if this is right, you can always check by taking the derivative, right? Take the derivative of this and you should get back to your original problem. If not, something's wrong. So just to show you that, if I took the derivative of f prime of x, the derivative of e to the 4x is e to the, well, the 4 gets to stay there because that's in the denominator. The derivative of e to the 4x is e to the 4x times 4. Those cancel. This pi is a constant, so that gets to stay there. The derivative of sine of pi x is cosine of pi x times pi. Pi's cancel. And the derivative of -2 cosine of 0.5x is remember the derivative of cosine is negative sine, so this is going to be +2 sine of 0.5x times 0.5, and the 2 and the 0.5 would cancel, and then of course the derivative of a constant would be 0, and what's left over is exactly what we started with, e to the 4x plus cosine of pi x plus sine of 0.5x. That will become a little more useful, I think, as we get into more and more complicated antiderivatives, knowing that you can check your answer with the derivatives. Okay. I want to give you another example of an applied problem. You didn't see much of that today. I think Dr. Burke was more focusing on the mechanics of taking antiderivatives and remembering certain formulas, but this is coming, okay? And in fact, there's some on your WebWorks homework, and I've already kind of told you, expect your quizzes and tests for the most part to be applied, not just find the antiderivative, but some kind of a word problem where you're going to have to find the antiderivative. So let's do one more of these, and then I'm going to switch over to finding area under a curve, which I think is going to be Friday's class. So let's say someone is given an injection of a drug, maybe a vaccine would be nice. And the concentration of that drug over time, what would you expect to happen to the concentration of a drug? I was just going to maybe think about this over here off to the side. Like if over time, if you get a one-time injection, and this is the concentration of the drug over time, you're going to immediately, all of it goes to the bloodstream, right? If it's an injection. And what would you expect to happen to the concentration of the drug over time in your bloodstream? Well, your body's going to process it, right? It's going to process it and then eliminate it from the body. So what I would kind of expect to happen is your concentration is going to kind of diminish slowly over time, something like this. Okay. And so what we have here is, I remembered I gave you one last time, but I'm not sure I defined this. This is called a differential equation. Where can I put that? Right here. All a differential equation is that it's an equation written in terms of the derivative of something, right? We don't have a formula for the concentration over time. We have a formula for how the concentration's changing over time, right? This is a derivative. So differential equation is the name for that. Also called, I think she used the term initial value problem. That's the same idea. I'll put or initial value problem, same thing. And I'll use DE because we're going to use differential equations a lot. So DE means differential equation. So we want to solve this differential equation for C of t under the assumption that there will eventually be no trace of the drug in the bloodstream, right? If you get a one-time injection, eventually your body's going to process all of it and it'll go away. All right. So because we have a derivative of of C, we want to find the antiderivative to get to C of t. I'm just going to rewrite this. So we have C, I'm going to write it like this, C prime of t equals negative 0.1 e to the negative 0.3 t. So to find the actual concentration, we're going to want to do the antiderivative. Okay, and so using what we've learned here, a constant times my function, the constant just gets to come down for the ride. The derivative, the antiderivative of e to something t, that was one of our practice problems, is going to be e to the constant t divided by that constant, which is really the derivative. And I just talked about how, for we call this the constant of integration, usually we use plus C, but maybe here's a situation where I don't want to use C because I might confuse that with concentration, right? So maybe I'll use plus K here. And I think I'm going to just rewrite this. If I combine these two, right, because this is just a constant over constant, the two negatives cancel, and 0.1 divided by 0.3, this is the same thing as 1/3. Okay. Now, in this, when you get these initial value problems, what we're going to want to do is take it a step further. This is the general antiderivative, but in order to be able to tell the concentration of the drug at any time, we need to know what that constant of integration is. And so the problems I saw at the end of class this morning, it was very apparent. They gave you the initial concentration or some information or the initial value. They gave you a point, basically. Sometimes in a word problem, you have to fish this out of the problem. And here's where we're going to find that information we need, right here. If we know that eventually there's going to be no trace of the drug in the bloodstream, what that's basically telling us is eventually, meaning like, you know, in the long run, right? That's like as over a long period of time. So that basically could be interpreted as the limit as t approaches infinity of the concentration of the drug eventually is going to come out to be 0. Does that make sense? And this is the part about the, you know, 17b is that makes it a little tough, is you have to kind of fish out that information. They don't just straight up tell you often. Okay. So we could now use this information to solve for that constant. Because I could now say, all right, now that I know this, if I took the limit as t goes to infinity of c of t, which was 1/3 e to the negative 0.3 t plus k, I'm supposed to end up getting 0. Well, how do we do these limits? We plug them in. So this is going to be 1/3 e. If I put in infinity and multiply it by negative 0.3, that's going to turn into negative infinity. And somebody tell me how to make sense of this. What is e to the negative infinity? You've probably seen that, I think, last quarter. That came up, I'm sure. Or better yet, maybe not what is that? What would it approach? Nice. Yeah, it's going to approach 0, right? Remember that e to the negative infinity, where can I write that? E to the negative infinity is really 1 over e to the infinity, which is going to not exactly equal 0, but it'll approach 0 in the long run. So this term goes away. This goes to 0. And if that term goes to 0, then this whole thing goes to 0. That means in this case, my constant of integration is just 0. Because I have 0 plus k equals 0. My constant of integration is 0. Therefore, a formula for the concentration of the drug at any time t is simply going to be 1/3 e to the negative 0.3 t. Again, k is 0, so that is it. All right, so I've got another. We'll do another one of these on Friday. Another similar type of a word problem, because I think I want to practice the things that I know you're for sure going to see. Maybe I'll do it as a poll question. There we go. Maybe I'll give you a poll question on Friday with a word problem there. Questions? Okay, if not, what I think I'd like to do, looking at the homework you're responsible for by sometime next week, there's more than just these types of problems. There are problems. This kind of gets into chapter 5 now. This is the next section, which I expect Dr. Burke to be teaching on Friday. This is section 5.1. And it totally shifts gears now. We are going to come back to antiderivatives, but for a few sections in the book, what we're going to concern ourselves with is finding the area or estimating the area under a graph. When I say under, that also means and above the x-axis. That's kind of so the square root graph looks like this. Between 0 and 16, what I want is to estimate the area under the graph, but still above the x-axis. If I can shade this in. I want an estimate for this area. And this is kind of the terminology you're going to see. The way we're going to estimate this is we're going to use 4 what we call approximating rectangles and right endpoints as what we call sampling numbers. So let me explain how this works. What we're going to do is take this, the x-axis, we're interested in the portion of the graph between 0 and 16. And because there's 4 approximating rectangles, what we're going to do is divide up from 0 to 16. We're going to divide this up into 4 equal sections. And what we're going to want to know is what is the distance between each of these, we call these subintervals, between here and here and between here and here. And we call that delta x. Delta x is the distance of each subinterval. Oh, this is too bright. Okay. Now, you probably can figure this out. If I take this total length, which is 16, and cut it into 4 pieces, what's the width? What is delta x going to be equal to? Just type it in the chat. What's that length? How far is it between each of those hash marks? Yeah, exactly. It's going to be 4, right? You're just dividing 16 by 4. So most of the time you can figure out what that width is on your own. There is a formula, and you probably should be familiar because of the terminology. So usually the left-hand number, we refer to that as A, and the upper bound on X is B. Your formula for delta X is B minus A divided by N. N being the number of rectangles. So in this case, N is equal to 4. So just to show you how that works, it would be 16 minus 0. That's the total length, and we're dividing it into 4 equal parts. So my delta x is 4. And what is that useful for is we can now actually come up with these x values. If I'm starting at 0 and I know this distance is 4, this would be 4, this would be 8, this would be 12, and then I've already got the 16. Now, what we mean by right-hand endpoints and how are we going to approximate this area? We're going to take, for this first subinterval between 0 and 4, we're going to take the right endpoint, the 4, and if you think of wherever the value of that function is when x is 4, goes straight up there, we're going to make a rectangle that comes back to, this 0 right here. And we're going to be finding the area. Maybe I need a different, I don't know if the different colors come through here. We're going to end up finding the area of this rectangle. Then for the next subinterval between 4 and 8, the right-hand number, the right endpoint is 8. So we're going to go straight up on the 8, come back, make a rectangle there, and we're going to find the area of that rectangle. And we're just going to continue to do this for all 4. And then here, the 16. If we find the area of those 4 rectangles, you have to agree it's a rough estimate for the actual area under the curve, right? Of course, Well, in fact, is it an overestimate or an underestimate? Well, clearly the rectangles are way more. We're getting more area than we really wanted, right? But nevertheless, it is an estimate. And so that's fine for right now. Now, how do we actually find the area? The first number that we use to determine the height of the first rectangle, we'll refer to that as x1. This is x2. This is x3. This is x4. So the areas of those four rectangles, let's talk about the first one. The first rectangle's area is going to be width times height, right? Or height times width. How do I find the height of this rectangle right here? Well, I just need to know what's the value of my function when x is 4. So in other words, I need to find f of x1, right? I need to find the value, the height of my function. What do I multiply that by? I multiply that by delta x. For my second rectangle, the height of it is given by f of x2. The width of it is given by delta x. And it's going to continue. F of x3 times delta x. And my fourth rectangle is f of x4 times delta x. So we've got height times width. Now we'll put in the numbers here in a second. But one thing you'll notice, what's common, what's the same for all of these? Delta x is the same, right? Delta x equals 4 for all of these. So to make the calculation a little bit simpler, what we could do is factor out the delta x. And then we're just going to do f of x1 plus f of x2 and we're going to put in the numbers now. Hang on, I'm finding something here. Oops. So if we actually put in the numbers, and you'll have to do this on WebWorks. So f of x1 means basically f of 4, which in this case would be the square root of 4, right? My function is the square root of x. This would be the square root of x2, the square root of 8, plus the square root of 12, plus the square root of 16. I know two of these are nice simple numbers, right? That's 2, that's 4, but these two you would need a calculator. So, but if you're doing WebWorks homework, you know that probably the best way to do this on WebWorks is just type it in this way. Don't, if you try to use a calculator and approximate it, it's going to probably maybe not give you the right answer. If you plug this into a calculator, you're going to get an answer of about, that's why I was pulling this up because I have the answer. It's 49.17. Oops. Okay. And just to acknowledge, this is definitely an overestimate of the exact area. Right. It's an overestimate because my rectangles go above the graph. Yeah, so what, explanation here. In this case, x1 was my first number, which was 4. Remember that my function is the square root of x. That was the function I had up there. So I would be plugging 4 into here. That's how I got the square root of 4. Same thing there. Yeah. Now that's an overestimate, and it's a pretty gross overestimate, right? So what else could I do to estimate this area? Is I could use left-hand endpoints to determine the heights of my rectangles. So we're going to do the same thing over again for the same function. And the notation you'll see in the book is L4. That means you're using left-hand endpoints and 4 rectangles. Let me show you what that looks like. Because we're using 4 rectangles, we're going to have the same numbers here. We're going to have 4, 8, 12, and 16. Give you a second to draw that down. I think it's going to be less confusing here if I start, let me start on the right. You can do it any way you want. So if I take this rightmost subinterval from 12 to 16, this time I'm going to take the left endpoint in that interval, and wherever that hits the function, I'm going to draw a rectangle coming back to the 16 here. Between the 8 and the 12, I'm going to take the left endpoint. Come back. I got a rectangle between the 4 and the 8. And now you can probably see why I started at the right, because technically right here at 0, if I take the left endpoint, the height of the function is 0. So I actually don't even get a rectangle, huh? It's more like a line. But now what I'm going to do is add up the areas of these. Well, I'll call them 4 rectangles, even though there's really 3. One of them has no height. And I'm going to use the areas of these 4 rectangles as an estimate for the area of the curve. And clearly now you can see that I'm not getting all of the area, right? I'm not capturing it all. So this is going to be an underestimate of my exact area. I'll put, here we go. Underestimate of now the process is still the same. The only difference though, so you can use the same formula. The way we would denote this though is the number we technically used for our first rectangle to determine the height was 0. So this now becomes x1. Our second rectangle's height's determined by the 4, that becomes x2. This becomes x3. And our last rectangle's height was determined by the 12, so that becomes x4. Notice it's different, right? When we did right-hand endpoints, we included the 16. Now we're just moving everybody over to the left one. But the same formula could be applied. It's still width, and then I would just be doing all of those heights. So this would come out to be 4. Okay, now we know it's the square root function. And now since I'm using 0, this would end up being the square root of 0 plus the square root of 4 plus the square root of 8 plus the square root of 12. And if you work that out, you end up getting 33.17 about. Oh, you can't see that. Ha ha. You're thinking the right way. I like that. Kind of. You actually are kind of right. Okay, so here's what we know right now. This was an underestimate of the exact area. The other one was an overestimate. So we know the exact area lies somewhere between 33.17, right? That was our underestimate. And what did I get for the last one? 49.17, right? So the exact area is between 33.17 and 49.17. But, you know, that's quite a big range, huh? If I wanted to be more precise, if I wanted to narrow this range of values, narrow this interval so that I knew the area was, you know, within 1 or 2 units from 2 numbers or something, what are my options? What could I do? If I wanted to be more precise with this. And I have 2 answers to that. One of them would be to use more rectangles. If I use more rectangles and they get narrower and narrower, I'm going to get a more precise answer. But it turns out there is another way. If I still insisted on only using 4 rectangles, Another option you can do is do a different choice. Besides right-hand endpoints and left-hand endpoints, I'm going to take a suggestion in the chat here. What if I kind of average the two? In other words, can I move this? I could use M4 stands for midpoints. Oh, I wrote it right here. Never mind. M4 means I'm going to use 4 rectangles and I'm going to use the midpoints of each subinterval to determine the height. So I am kind of averaging between the right-hand endpoints and the left-hand endpoints. So like, here's what I mean by this. If this is 4, 8, 12, and 16. What I'm going to do now is for the first subinterval between 0 and 4, I'm going to find the midpoint. And that's pretty easy to find, right? Between 0 and 4, my first midpoint is 2. How about I call this, instead of x1, I'm going to call this m1, okay, which is equal to 2. 2. Maybe I need a different color here. The next midpoint here we'll use for our height is going to be halfway between 4 and 8. That is 6. 10 is halfway between 8 and 12, and our last midpoint is going to be 14. And the idea is now is the midpoint's going to determine the height of the rectangle. So whatever the value, the height of this function is at 2, I'm going to draw a rectangle, however, that goes all the way across from the 0 to the 4. Okay, so I'm going to use this rectangle between 0 and 4, whose height was determined by the midpoint. And you can see what's kind of nice about that is, think about just this one rectangle right here. Part of the rectangle overestimates the area, right? It's above the graph, but the other part is underneath the function. So that's an underestimate. And you can almost imagine this over and this under kind of balancing each other out, right? In terms of getting a more accurate idea of what the actual area is. So it's midpoints are really useful for getting a more accurate answer. Let me just draw these for the rest of them. So then when, for the midpoint here at, what was that, a 6, I'm going to have a rectangle here at 10. And we're just going to end up finding the areas of those 4 rectangles. One nice thing about this section, it is pretty logical, intuitive. If you know you're just finding the areas of rectangles, all you got to really do is, follow the directions on how many rectangles you want and what convention they're using for determining the heights of the rectangles. But other than that, it's just finding the area of 4 rectangles in this case. So it is kind of one of the few places in 17B where it really is kind of intuitive. All right, so same formula though. There's 4 rectangles. So what we're going to be doing is multiplying delta x by, in this case, the value of our function at each of our midpoints, f of m1 plus f of m2. Delta x is still 4, but now we're going to be doing, for the square root function, it's going to be root 2 plus root 6. No, plus root 10, not root 8. Root 10 plus root 14. And that comes out to be, I've got an answer for that. I don't want to waste time with calculations. That comes out to be, do I have it? Oh no, do I not have it? I have it. It's about 43.07. And And to be clear here, this is definitely more accurate, but it is not the exact area. More accurate. I think accurate has two C's. Sneak another one in there, but not exact. And then maybe I'll close with this last one here. So midpoints work out nice. That's definitely more accurate than using four rectangles with right-hand endpoints or left-hand endpoints. But another way you can get more accurate is to just use, you can stick with right-hand endpoints or left-hand endpoints, but just use more rectangles. And when you draw the graph, you'll see why that works. So R8 means 8 rectangles, right-hand endpoints. So I want to split this region up now into 8 equal parts. So let's start with 4, and then I'll just go cut these in half. What that does change, of course, is your delta x, because your widths now are more narrow. It's going to be 16 minus 0, right? Remember, a minus b divided by 8 this time. Your delta x is going to be just 2. So this is 2, 4, 6, 8, 10, 12, 14, and 16. And if I use right-hand endpoints, I'll just try to sketch these in. You can start it and finish it later if you want. This takes a little while to do this. Okay. What I want you to hopefully see is that I do have more work to do, because now I have to add up the areas of 8 rectangles, but that's not too, we could do that, right? With time and energy, we could do that. This is still going to be an overestimate because my rectangles I'm not spelling correctly, overestimate, but it's going to be better than our very first example when we used 4 rectangles. It turns out that this, our error is going to be how much each of these rectangles jets out above the graph. But it turns out that the sum of these, all 8 of those little areas, is still smaller than, this was our picture when we did 4 rectangles. It's still smaller than how much those 4 rectangles jet out over our curve. So this is going to be a better estimate of it, right? So let me close with this then. If using 8 rectangles gives you a more accurate answer than using 4, what would be better than even 8 rectangles? If I wanted a more accurate answer, how many rectangles, what would be better than 8? Oh, you went straight to it. Good. Yeah, I was thinking like 16 or 30. But yeah, what would be the ideal way to do it, right? Is if you could somehow fit an infinite number of rectangles in there. Maybe I could kind of sketch that out, right? Imagine if you could put an infinite number of rectangles in there, what they would become is infinitely thin, right? And the amount that each rectangle stretches out above the curve would be infinitely small, right? If these were infinitely thin. But what would be the challenge now? What would be the hard part? Oh, yeah. What would be the hard part? If I could fit, certainly I could fit an infinite number of rectangles between 0 and 16, but what would be the hard part? How many people agree adding up the areas of an infinite number? Yeah, I like that. Adding up the areas of an infinite number of rectangles seems like an impossible task. How many people agree with that? That would just seem like an impossible task. What if I told you that in fact, we are going to be doing that? We will be able very soon to have the skills to be able to add up the areas of an infinite number of rectangles. And that's kind of the coolness of calculus when you can do crazy things like that. We're out of time today though, so we won't do it today, but that's coming up. So give you a little preview of coming attractions. All right, I'll stop the recording. As promised, I will stick around.